Welcome to the 19th video of Quantum Mechanics Done Right, the shortest path from novice to researcher. In this video, we're going to talk about the advanced math interlude, where we focus on matrices, primarily matrices of arbitrary size, as opposed to the 2x2 and 3x3 matrices that we've been working with up until now. Chapter 13, Advanced Matrix Properties. So we're going to really cover the mathematics for matrices. We'll look at the eigenvalue and eigenvector problem in general, now that we have arbitrary n by n matrices that we'll be working with. We'll look at the interesting properties of matrices, such as the determinant, the trace, and the partial trace. Partial trace becomes very important when we look at decoherence. We'll look at functions of matrices. These are easiest to understand when you're in the diagonal eigenvector basis. In that case, you can just apply the function to the diagonal elements of the matrix. We'll look at a matrix absolute value, which is a special function. It's the square root of the square of the matrix. And we'll talk about what positive semi-definite matrices are, which is a very important class of matrices. When you can establish that a matrix is positive semi-definite, there are lots of interesting things that arise as a consequence of that positive semi-definiteness. As you recall, when we do factorization method, we put the Hamiltonian into a positive semi-definite form, and that then allowed us to determine what the ground state was. There are similar kinds of ideas that arise here when we talk about positive semi-definite matrices. We then switch gears, go away from matrices, and we look at how you can do summations of exponentials, cosines, sines, and powers. This becomes very important in looking at a number of problems that we have to do with time evolution. And then we conclude with a chapter that looks at how the Born rule can be related to counting. And it's a really cute argument that motivates why the Born rule is what it is. All right, guys, let's go browse through the chapter. Our quote for this chapter comes from a wonderful artist, Jacob Lawrence, who says, "When the subject is strong, simplicity is the only way to treat it." And I think that even though Jacob Lawrence is an artist, I think that the spirit of that quote is really important for science. Einstein had a quote of, "Make things as simple as you can, but no simpler." And this is a similar spirit of that Einstein quote. So we start by talking about what happens as we go from 2x2 matrices to n by n matrices. The arithmetic is essentially the same. If we add matrices together, we do it element-wise. If we multiply them together, we use the matrix product rule. We talk about the fact that these n by n matrices will have inverses if their determinant is non-zero. And we'll also talk about how you can relate matrices to Dirac notation and discuss again what Hermitian matrices are and unitary matrices and so forth. We will also look at what are called similarity transformations, because it's important to understand what a similarity transformation does to things. The fact that a determinant and a trace are invariant to the similarity transformations is an important property of matrices. We have a number of exercises to help you practice these properties and new ideas with matrices. We then talk about determinants. A determinant is a really odd construction if you've never seen it before. It isn't the kind of a thing that you would think about working with. But it turns out determinants are really, really powerful. And we discuss a lot of the properties of the determinants. And these properties of the determinants are what makes them powerful. In particular, the determinant of the product of two matrices is the product of the determinants of the two matrices. And when a determinant is non-zero, then the matrix will have an inverse. And these are all quite important results. We next move on to talk about eigenvectors and eigenvalues in general. It's the same kind of problem, but now it becomes too difficult to try to carry it out by hand. except possibly for 3 by 3 matrices. So in general, when we have to solve this problem, we have to do it numerically. There is a special class of matrices called non-negative matrices, not the same as positive semi-definite. They're non-negative matrices, for which there's a theorem called the Perron-Frobenius theorem that tells us something about the eigenvector that has the largest eigenvalue. And that is a very important theorem that we'll use a number of times to prove different results about problems that we're working on. After that, we talk about functions of matrices. We often are taking exponentials of matrices, so understanding in detail how we do that for n by n matrices is a really important problem to look at. Then we get to one of the important functions, which is the square root of the square of a matrix. That's called the matrix absolute value, and that also is a really important matrix to understand. It is a positive semi-definite matrix, so understanding the properties of positive semi-definite matrices is also an important thing that we talk about. Then we get to trace. Trace is just the sum of the diagonal elements of a matrix. Interestingly, it is invariant under a similarity transformation, and it also is invariant when the trace of the product AB is the same as the trace of the product BA. That is somewhat surprising, but true. There's also a relationship between determinant and trace, which is quite interesting as well. We then go on to talk about really the most important linear algebra fact for quantum mechanics, which is called the spectral theorem. It's about completeness and orthonormality of the eigenvectors. And for any finite sized problem where I only have a discrete number of states n, this problem is a classic problem in linear algebra. When you get to an infinite sized system, it's a much harder problem, and that's what requires you to get into Hilbert space theory. We, of course, are not going to get into those kinds of details. That's a very advanced topic in mathematics. But it turns out that all of the problems that we work with, they satisfy these completeness relationships. And so we do freely use them, as we have been using them throughout the work that we've been doing. Then we get on to this section. We move off of matrices and we talk about summations of exponentials. You can see here that the exponential, if I'm summing an exponential over values of time that are linearly spaced, it looks just like a geometric series, and so that allows me to do the summation. And using this trick, I can also then do summations of cosines and sines by adding an I into the exponent and taking the real or imaginary part. And then the other thing that we need to look at summations of are powers. And there's this really neat trick that allows you to work out what the summation of powers are. There's a very cool trick that works when you're looking at the sum of integers themselves, but once you start looking at the sums of powers of integers, it gets a little bit more complicated how to work it out. But it's a very straightforward technique that you can actually work out, and it's pretty cool to see how that works. Again, that is the kind of a thing that we're going to need for some of the problems that we're going to be working on, particularly in time evolution. If you're a purist, I'm teaching you a little bit about integral calculus here, but you don't need to know anything about integral calculus to do the kinds of things that we're doing. And then our final section is using a counting approach to talk about the Born rule. It's related to a theorem called Gleason's theorem, which was proved all the way back in the 1950s. And it's a really cute argument that shows you why you need to take the modulus squared of the quantum state to the amplitudes of the expansion of the quantum state to tell you what the probabilities are of finding that particular quantum state if you do a measurement. And that's the end of the chapter. Hey guys, let's do quantum right.